Welcome to equilibrium expressions involving pressures. So, thus far, we've discussed equilibria in terms of concentrations, so molarity. But we can also discuss equilibrium in terms of pressures. So, if we're working in the gas phase. So, the relationship between pressure and concentration can be derived from the ideal gas law, PV equals nRT. If we rearrange PV equals nRT to give us pressure, P is equal to N over V times RT. Well, N over V is concentration. So remember, N is the number of moles, V is the volume. So if we are looking at, say, moles per liter, well, that's N, number of moles, divided by a volume, liters. So that's a concentration. So this quantity, N over V, can be replaced by C, the concentration. And that means that now we have pressure is equal to CRT, where C is the concentration that we have. So in this case, it's a molar concentration. Now, if we denote the equilibrium constant in terms of concentrations, Kc, K sub C, then we can write the equilibrium expression for the formation of ammonia. So the formation of ammonia is given here. So we have nitrogen gas reacting with hydrogen gas to give us ammonia gas. So we can write this in terms of concentration. So Kc is equal to the concentration of ammonia squared divided by the concentration of nitrogen gas to the first power times the concentration of hydrogen gas to the third power. And we could write that instead of with these brackets around our species symbol, our chemical symbol, we could write that this way with C's, C standing for concentration, and then a subscript of whatever the chemical symbol is, so CnH3 squared, or Cn2, or CH2 cubed. And then if we solve the expression from the ideal gas law for the concentration, that gives us C is equal to P, the pressure, divided by R times T. R is the gas constant, T is the temperature. And then we can substitute these expressions involving the pressures into our equilibrium constant expression involving the concentrations, and that then gives us this big guy. But now notice that we now have pressure divided by RT. In this case, it happens to be squared. We've got then that divided by a pressure divided by RT. All of our pressures are going to be divided by RT, which means that we can group together all of our pressures and we can group together our RT terms. And note here that because we've got 1 over RT for each of our pressures, we're now taking the RT terms from the denominator and placing them in the numerator, and taking the numerator, putting it in the denominator, removing the inverse, because here we have the inverse of RT, so we're putting that in the denominator there. And then we're simplified, going from here to there, so that we end up with RT squared times our pressure terms. And now we have the pressure of ammonia squared divided by the pressure of nitrogen times the pressure of hydrogen cubed. And so it's a similar sort of expression. This one here is similar to the concentration expression that we have, except that basically in place of the concentrations, we've plugged in the pressures, and then we have this extra term here, the RT squared. Note that in this case it's RT squared. If we have a different equilibrium expression, we may have a different power here on our RT term. It may be RT to the first power, it may be RT to the third or fourth power, it may be a negative exponent there. So it depends on what reaction you're looking at and what sorts of powers you have on your reactants and products there. So now we can combine our Kc, our equilibrium constant in terms of concentrations, and the RT to the N, whatever N happens to be, factor into one constant, the Kp, the equilibrium constant in terms of pressures or partial pressures of our gases. And so now we can then change from Kc equals our pressure expression times our RT to the n. We can wrap that RT to the n in with our Kc, our constant, our equilibrium constant there, and give it a new name. Now we're calling it Kp instead of Kc. So this is the equilibrium constant in terms of pressures instead of equilibrium constant in terms of concentrations. And note here that in this case, Kp is equal to Kc divided by RT squared. For other equilibrium constants, the relationship between Kp and Kc will have this form, Kc over RT to the n, whatever n happens to be. So again, here note that the power on RT depends on the coefficients that we have in the balanced equation. If the coefficients for the reactants and the coefficients for the products, if the sums of the coefficients for the reactants and the sum of the coefficients for the products are the same, then the RT term there has the n value is 0. So that was equilibrium expressions involving pressures.